Today we will discuss about natural numbers. We are going to study real analysis, then you should be very clear about what is real numbers. Real numbers are the collection of numbers consisting both rational numbers and irrational numbers. Then I can ask you a question, what is irrational number? Then you will tell they are the numbers which are not rational. Then the next question will be, what is rational numbers? Then you will tell that rational numbers are the numbers of the form p by q, where p and q are integers and q not equal to 0. Okay, then what is integers? Integers are the collection of numbers consisting of natural numbers, 0 and additive inverse of natural numbers. Then what is natural numbers? It's a simple question, isn't it? Everybody knows what is natural numbers. The numbers 1, 2, 3, etc. We are going to define natural numbers. Okay, this is one way of defining natural numbers. There are many other ways are there. We are going to define natural numbers through axiomatic approach. So what is axiom? If you are playing some game, you have to fix some rules first. For more mathematically, we can tell that axioms are the non-facts which we are not going to prove. So we will fix that axioms. Actually, the important thing of axiom is you need not try to prove the axiom. If you can prove that one statement, it cannot be axiom. Okay, so let us see that one. We want to list out some rules which is true for natural numbers and only for natural numbers. So my first rule is very simple. 1 is a natural number. Okay, it is obvious that 1 is a natural number, and we are sure that we cannot go with this axiom alone. We require one more axiom. That axiom is, if n is a natural number, then n plus 1, the successor of n, is also a natural number. So can we construct all natural numbers with these two rules? Some of you may feel it is okay. 1 is a natural number, then 1 plus 1 is a natural number. I will call 1 plus 1 as 2. 2 plus 1 is also a natural number because 2 is a natural number. So 2 plus 1 I will call as 3. 3 plus 1 is a natural number. I will define 3 plus 1 as 4, like that. But there is a small problem in this method. 1 is a natural number, all other natural numbers I am defining. So suppose I define 4 plus 1 equal to 1 again. What will happen? Then you will end up with this collection 1, 2, 3, 4. This collection 1, 2, 3, 4 satisfies the two axioms. 1 is a natural number. If n is a natural number, n plus 1 is a natural number. Because 1 plus 1 you define as 2, 2 plus 1 you define as 3, 3 plus 1 you define as 4, and 4 plus 1 just now you defined as 1 again. So you will not get the complete natural numbers. So what we will do? We require one more axiom to avoid this situation. That axiom says 1 is not the successor of any natural number. That means you cannot write 1 as n plus 1 where n is a natural number. So we have three axioms. Again, what we are going to argue is these three axioms are not sufficient. Okay, just now what we told, if you define 4 plus 1 as 1, you will end up in some problem. So I cannot, that is why I brought third axiom. These three axioms, can we prove that 4 is not equal to 1? It is very easy, because 4 is 3 plus 1. That means 4 is the successor of 3. If 4 equal to 1, what will happen? 4 will be the successor of 3 and 1 is also will become successor of 3. But our third axiom says that 1 cannot be successor of any number. So 1 I cannot write 3 plus 1. So 4 will never be equal to 1. Now you may feel that okay, we can proceed with only these three axioms. Is it possible? Let us see one example. Earlier problem was 4 plus 1 we define as 1. Then we arrive at some problem. So I cannot define 4 plus 1 equal to 1. But what happens if I define 4 plus 1 equal to 4 again? Then again this set 1, 2, 3, 4 satisfies all the three axioms which we have mentioned. You are not going to get the whole natural numbers. Then we require one more axiom. What is that axiom? Different natural numbers have different successors. That is, if n and m are different numbers, then n plus 1 will not be equal to m plus 1. How it will help you in constructing the natural numbers? Let us see. Suppose you want to prove that 5 not equal to 3. We will do the proof in contradiction method. Suppose 5 equal to 3. Then what will happen? 5 is successor of 4 and 3 is successor of 2. So 4 plus 1 equal to 2 plus 1. Just by the fourth axiom, different natural numbers have different successors. That is, if successors are equal, the numbers are also equal. That is 4 equal to 2. Again, 4 is successor of 3 and 2 is successor of 1. So 3 plus 1 equal to 1 plus 1. Again by fourth axiom, 3 will be equal to 1. But what is 3? 3 is 2 plus 1. So we got 2 plus 1 equal to 1. That means 1 is the successor of 2, which contradicts our third axiom. So we arrive at a contradiction. Therefore, this 5 equal to 3 is wrong. So 5 is not equal to 3. So we have 4 axioms. Do you believe that with these 4 axioms you can construct all natural numbers? Let us see. Look into this collection: 1, 1.5, 2, 2.5, etc. This collection satisfies all the 4 axioms. You can verify. 1 belongs to this collection. If n belongs to this collection, n plus 1 also belongs to this collection. There is no number in this collection such that whose successor is 1, and different numbers will have different successors. But you know that this is not natural numbers because it contains half numbers. So I require one more axiom. So I want to look into some rule or axiom which will fail in this collection but hold in natural numbers. Let us see one interesting thing. Can you prove 1 plus 2 plus n equal to n into n plus 1 by 2 in the above set? You remember the proof of this one. There are various proofs are there, but in your class 11 you might have learned a beautiful proof for this one. First what you will do, you will prove the result for n equal to 1. Then you will assume the result is for n equal to k. Then using that assumption you will prove that the result holds for k plus 1, n equal to k plus 1. Can you try to prove this result for the above set? That means the set containing half numbers. So you will see that it is not possible. So that gives a idea for the fifth axiom, principle of mathematical induction. That is, generally I can tell that natural numbers must satisfy principle of mathematical induction. That is the fourth axiom. Or a collection satisfying the principle of mathematical induction is natural numbers along with the other four axioms. So we have 5 axioms. So this 5 axioms together is called Peano's axioms. So I can define natural numbers as a collection which satisfies Peano's axioms. Similarly, there are various ways to redefine natural numbers. This is one method. So natural numbers are the numbers collection which satisfies Peano's axioms. Okay, now we have natural numbers. Next, my job is to add two natural numbers. Adding a natural number with 1 is very easy, because you know that if n is a natural number, n plus 1 is a natural number. So if I have 5, 5 plus 1 is there, it is a natural number, and you call it as 6. So that is very easy. But suppose you are supposed to add 4 plus 3. What will you do? 4 plus 3 I can write as 4 plus 2 plus 1, because 3 is successor of 2. So if I am able to find 4 plus 2, then 4 plus 3 will be the successor of 4 plus 2. So finding 4 plus 3, the problem of finding 4 plus 3 reduces to finding the sum of 4 plus 2. But how to find 4 plus 2? 4 plus 2 is successor of 4 plus 1. But I know what is 4 plus 1. 4 plus 1 is 5. Successor of 5 is 6. So 4 plus 2 is 6. If 4 plus 2 is 6, successor of 4 plus 2 is 6 plus 1, which is 7. So 4 plus 3 is 7. This is how you define addition of natural numbers. Now the question is how to multiply two natural numbers. Okay, so we will fix a rule for multiplication. Let m be a natural number. The first thing what I am going to say is 1 times m is always m. This is my definition. 1 times m is equal to m. Now, if you want to find n plus 1 times m, n plus 1 times m I will define as n times m plus m. So if I know n, what is n times m, then I can find n plus 1 times m. So preliminary what I should know? I should know what is n times m. Suppose n times m is defined, then n plus 1 times m is equal to n times m plus m. Let us see one problem here. If you want to find 4 times 3, 4 I can write as 3 plus 1. So it is 3 plus 1 times 3. By the definition, 3 plus 1 times 3 is 3 times 3 plus 3. If I know what is 3 times 3, my problem is solved. So what is 3 times 3? 3 times 3 is 2 plus 1 times 3. It is defined as 2 times 3 plus 3. So what is 2 times 3? 2 times 3 is 1 plus 1 times 3, which is equal to 1 times 3 plus 3. But 1 times 3 I know. 1 times 3 is 3. So 2 times 3 is 3 plus 3. it is 6. So moving backward, you will get 4 times 3 is 12. So this is how you define multiplication of natural numbers. So this is the books we have referred, especially Terence Tao. Try to look into that book also. Thank you.